Swayam Prabha. Digital India. Educated India.
Good morning everybody, and let us discuss about this ongoing topic on the surface roughness. So, we started the topic in the last class and we have seen that there are different components available and there are many different instruments also available. So, we have to select some components depending on the what is the requirement of that particular component which we are machined from the workpiece. And then we have seen that different machines are available or instruments are available which can be used for measurement of the surface roughness. And we also found that non-contact type and atomic force microscopy based instruments are good for the measurement of surface roughness on the micro components. So, let us go further on this day. So, we have seen this particular slide in the last class and these are the different properties of the or the specifications of the instruments. So, depending on your requirement you have to select this particular specification and then select the work instrument which we are going to use. So, what things are there in the surface roughness? The surface roughness damage is mostly done by the forces, because if you see this particular figure here what is going to happen. So, here you are getting burrs. So, these are the burr formation. So, these are the burr formation here, these are the burr formation and this is the surface. So, if you see this surface you are actually getting some type of machine marks. So, these are the milling cutting marks and whatever the spacing is there, that spacing will create a problem at the later case. What we need, that we do not need those type of marks and we do not need any type of projected material. So, this is the vertical wall. So, this is the vertical wall and this is the bottom surface and this is the wall surface and this is what is the component of the unmachined surface, side surface. So, in this way one is the forces. If the forces are very high or fluctuating forces, then you will get a different patterns and there is a burr formation also and there is a surface roughness increase also. Another thing is the vibration, because if your force is your workpiece is not clamped properly or your tool is not clamped properly on the spindles tool spindle, at that time you are getting a vibration. And if you are machining some type of heterogeneous material, then again there is a vibration in the machine. So, this vibration also creates surface roughness very high. Plastic deformation also create a problem, because what is going to happen, that your material will be, if you are machining a brittle material, your roughness will be mostly sometimes very smooth, but in machining of a ductile material like aluminum, it is very difficult to maintain or getting a good surface finish. And burr formation is obviously related to the surface. The higher the burr formation, higher is the roughness. So, this both things are coupled with each other. So, high surface roughness are mostly elastic recovery, because when you are cutting a material, we have seen in that lecture where we have seen that what is the condition when you are machining with a low depth of cut, but the high cutting edge radius. So, in that case mostly it is elastic recovery, your tool will just pass through the surface without removing any material. So, that is the problem with the high roughness. Elastic recovery depends on the size of the cutting edge radius and the workpiece material, because we have seen that you have to continuously monitor the status of the cutting edge radius with respect to the uncut chip thickness or the depth of cut. Material also play important, because the soft materials have the high elastic recovery compared to the brittle material. Large elastic, that is mostly when your cutting edge radius is very large, at that time it will create a problem, because it will just pass through the surface and you will not get any type of further improvement, right. So, what is the general scenario? The sharper the cutting edge, better is the surface finish, right. So, because we want to avoid the plowing action, if your surface or the cutting edge is very dull, at that time we know that it is not maintaining its value with respect to the uncut chip thickness, and because of that you will end up with rubbing and plowing type of mechanism and you are not getting the better surface finish in this case. So, we have to maintain the sharpness of the cutting edge for a longer time. So, there are many ways that if you set a process parameter very efficiently or optimize, then you will retain this thing. There is a coating also available, you can use cooling coolant also. So, these are the different ways you can maintain that part. So, material properties, microstructure and hardness, that we have seen that if it is a soft material, then your surface roughness is high, and if it is a brittle material, you can get a good surface finish. Then what is the material property? That for small tool, what is the problem? That its stiffness is very small, and the tool deflection is very high, because when you are cutting a material, then you are end up with the high vibration and finally the high roughness. So, this is the problem with the small cutting tool. If you use the bigger cutting tool, what we are using in the macro machining, at that time your stiffness is not a problem, because material has a very large amount of volume available. So, which will make sure that it will not deflect to a certain level and you are not getting a vibration in that. And this is the things in terms of the surface roughness. Now, here what is important things, there are two different tools, one is the 600 micron and there is 900 micron, and there are three different cutting tool material, that workpiece material. So, this is the things. So, if you see this particular thing 600 micron, if you see this is the 600 micron for machining of brass and 600 micron for machining of a aluminum. Now, if you see that aluminum is very ductile material, so its roughness is also very high in this case. And another thing, that smaller the tool, higher is the roughness, because we know that smaller the tool, what is going to happen, that because of this sequence of this particular event, you are getting a high surface roughness. Other than that, we also know that a smaller the tool, your means consistency with respect to the uncut chip necks, that is the relation between these two is more and more tight. So, you have to also maintain this particular relation if you are going to use very small cutting tool. So, that is the reason that you can see that with a 600 micron, all the results is giving, or results are giving more surface roughness, but when you are going with a bigger size cutting tool and keeping all the parameter constant, then you are end up with a small surface finish or the small surface roughness. So, in this case, you can see the brass is giving much better result compared to the other two material, because in the steel material removal, because we know the harder the tool, our tool wear is also very high. So, it is not only case of the material, ductile material, but we have to also see. So, in brass is something in between these two. So, you are actually optimizing with respect to material, that going to with a hard material, your tool wear will be very high, and at the end your material surface roughness is very high. Compared to aluminum, aluminum is soft material. So, your tool wear is not a problem, but the chip clogging is problem, then the material removal is also problem, you have elastic recovery. So, those things play important role in the surface generation mechanism. So, this is diagram what it is showing, right. So, this is what is the chip. So, now if you see the condition of the cutting tool, now when you cut a steel material, you can see that there is no chip clogging on the flute of this cutting tool. But if you see aluminum, there are many chips which are actually stick to the surface, and these particular chips are creating problems. So, now if you use this cutter, yes, chip will not get the flow or the passage through which it will come out of the socket or come out of this particular pocket which is going to cut in this. And this is in between these two, because here if you see very small amount of material is loaded in the flute, but this material may be removed if you rotate at a very high RPM, but nothing is here, but the tool wear may be very high in this compared to the other two materials. So, this is the condition of the cutting tool after machining of three different type of workpiece material, right. So, these are the property of this particular material. So, now if you see in this, elastic module is important, yield stress is important, hardness is important. If you see this particular material, so these are the three particular things, and then this is the hardness is here, and this is the yield strength is here, correct. So, depending on if it is a very low, it is also problem, if it is very high, also it is a problem. In between, it is giving a optimized result, correct. So, here the tool wear is a problem, and here it is a material removal is a problem, correct. So, this way, because anyhow you have to cut the aluminum, but you have to finalize the process parameter in such a way that you are not end up with this. You use some type of mist coolant and you add some type of projector with a high pressure, so that it will remove these things very easily, right. So, here it is the tool wear. Now, if you see this particular thing, so this is the tool condition after 15 minutes of use, and this is after 30 minutes and after 45 minutes. Now, if you see, this is mostly the rotation is in this direction of cutting tool, and then it is moving in this direction. So, now this is the up milling side and this is the down milling side. You can see that in earlier case also we have seen that the two chip formation, that means the burr formation on the down milling is high compared to the up milling. So, this is the condition after 15 minutes, and after 30 minutes what is going to happen, that your cutting tool also getting worn, and because of that you are end up with getting more and more top burrs on the both the surface. Now, the size of this burrs on the bottom or the down milling is high, and you have also getting burr in the up milling side. If you further increase that particular cutting tool for operation, then you can see that there is a large amount of wear of the cutting tool, and the size of the burrs are also very large in both the cases. So, now you can see that by tool wear you are getting worst and worst condition of the workpiece material. So, now for getting a surface finish is also important, because here the surface, if you see here in this location, surface is very fine, and now here you are getting some type of problems here. So, these are the residual material which are staying, and then you are getting marks also. So, these are the marks, and when you are ending with this worn tool further, using this worn tool further, then your roughness is also very high, correct. So, you are getting both the things. The higher the tool wear, high surface roughness, and the high burr formation. So, you have to estimate the tool wear, that is very important in this particular case, because if you do not look into tool wear and you continue the machining, your workpiece will not be acceptable at the end. And sometimes what happens, that here you can apply deburring operation very conveniently, but here deburring is also very difficult, because size of the burr is so high that you have to use some aggressive deburring operation, and that aggressive deburring operation will actually create a problem at this finished surface also, or the machined surface also. So, it is better to limit the use of the cutting tool within a short period, or you do some type of coating and use coolant, so that you can increase this particular life to a certain further duration. So, what are the key aspects of the machining? What we have learned, that we have three different areas by which we can monitor or we can understand something. First is the workpiece material, and we have seen the grain size is important, because smaller the grain size, easy to remove material, because the cutting tool will pass through the boundary of the grain. Hardness is playing important role, because hardness you are getting a good surface, but your tool wear is very high. Homogeneity is important, you will not get the fluctuation of the forces. If the presence of defects is very high, material removal is easy, but what is going to happen, that your workpiece will not be acceptable at the end. Impurities, that is same material with a different size, you will getting different parts. Built up edge is also a problem, because if built up edge is there, then your tool will not penetrate much, and it will create some type of stick slip type of phenomena. Elastic recovery is important, because if it is a low, then you will get a removal very easily. In terms of tooling size, because these are the three things which are very important in our cases. What material we are using, that is important. That means we have high speed steel, we have tungsten carbide, we have ceramic tools. So, those things are very important, and we are very more concerned about the edge radius, because sharper the edge radius, we can easily remove the material, and now we can give a small depth of cut depending on the sharpness of this part, because we have to maintain that particular radius. The HC should be higher than the RC. So, that is the uncut chip thickness or the depth of cut, and this is the cutting edge radius. Correct. Grain size of that thing is important, because we are using a very small tool. Correct. So, this is considered a very big tool, we are using in a micro machining. So, it is considered as a 10 mm, right. So, we are using a very coarse grain of this cutting tools, tungsten carbide, let us consider it did. So, now if you go from here to 100 micron, then if you same thing, what is going to happen, that only 2 or 3 grains will come into this particular part. So, that means its strength is also very less. So, you have to use very fine grain tungsten carbide particle in such a that you will get a enough amount of particles to maintain that stiffness for a longer time. Coating is important, batch consistency. Suppose that you are making 10 cutting tools, then all 10s are with the same quality or not, because machining process itself is creating a problem at the later stage. Then coming to the machine tool, that you cannot get the micro machine component from all the machines. So, you expect some type of reasonable good specification from the cutting tool, machine tool, so that it can generate a micro machine. The spindle speed is important, you have to go with higher cutting speed, so that you have a reasonable amount of production rate. Run out is very problem, because cutting a material with a very high run out of the spindle, you are end up with the sudden failure of the cutting tool. Position accuracy, that we have seen in the geometric accuracy or the geometric error in the x, y, z and other directions. Response time is important, because when you give a command, how much time it requires to act on that command by the cutting tool. So, that is important. Stiffness is important, because it should maintain its structure in a firm way under the action of different type of cutting forces. Damping is important. Higher damping will reduce the vibration to propagate into the different components. So, that is important. Thermal stability, these things we will discuss more detail in the spindle part. So, thermal stability is very important, because if you are getting a large variation in the temperature, all components have a different coefficient of thermal expansion. So, material will expand in a different direction with a different magnitude, and then your structure will be deformed completely. Error compensation is important, because if your structure, we have seen in that video also that there is a error compensation with a 0.1 micron in a one machine tool company. That is that if you can calculate the error compensation, then if you are going to target this particular, your tool is located here, then what is going to happen, that once the temperature is different at different part, your machine sensor, temperature sensor will calculate those temperature differences, and that temperature differences will be transfer into the motion controller, and motion controller will again target this particular part to the actual location. So, at that time error compensation, that is related to temperature compensation. Other than temperature compensation, there are different sensors available which will do also the position compensation, even if there is some type of deviation. So, our focus is on the workpiece material. You cannot cut any material in the micro machining, you cannot use any tool for the micro machining, and you cannot use any machine tool also for micro machining. So, you have a specific combination of all the 3 components, then only machining at micro scale is possible, right. So, what are the summary of this differences, that workpiece principle is mostly same, material is removed, but there are differences are there. One is the material is removed by the micro tools. So, you have to end up with, or you have to fabricate this micro tool. So, that is also one of the process, because when you are cutting at a micro scale, you are using a micro cutting tool, but you have to also find some processes which are fabricating this micro tool. So, those processes are again the machining processes. So, again the requirement is very tight to these processes. So, that is the one thing. Feature size can be in the range of few micron to hundreds of microns. So, these things are different than the conventional machining, and very important things are the specific cutting energy is very high, because at small scale you are getting very less amount of defect. Material strengthening is also very high. Minimum cut chip thickness, this you have to maintain, otherwise you will not get a clear material removal. Plowing, rubbing, those things are very frequent in the micro machining. Surface roughness, you have to pay more attention to this, because surface finishing application is very difficult here. You can apply a deburring operation, but surface finishing operation is very difficult here, because burr size is very large compared to the roughness component. If you are removing the burr, it is very easy, because still it has a micron size or something, but when you are looking at the surface roughness, it is always a nanometer size. Microstructural effect is important, because what is the microstructure of the component which you are machining. So, it has different component. Tool wear is very important. In micro machining, what is mostly happen, there is a tool breakage is more frequent. Breakage is more frequent than tool wear, because even a slight amount of change in the force or different other force, other parameters, your tool will suddenly break before it will reach to the wear. So, calculation is wear is not important, calculation that how to avoid the breakage, that is more important. If you can avoid the breakage, then you can do some measurement of wear, but if your tool is getting broken within 1 minute, then there is no way of paying more attention to the tool wear. Modeling is very difficult here, because whatever theory we have learned in the merchant circle diagram, force measurement, those things are not directly applicable to this, because you have to do lot of modification, because these parameters are completely different. Sensing and monitoring methods are very important here, because these particular things, because everywhere we know the forces are very low. Right, forces are low. So, this is very big problem, and sometimes you will not get any type of voice out of that, means there is no any type of noise or some machine disturbance things from that. Visual confirmation is difficult, visual access difficult, and other than that, you do not have less wall space available, because space also you do not have here, because suppose you want to add some microscope or the high speed camera or something, how you can focus to that location, that is also different, because at macro scale you can easily get the idea of the focus on the chip and that workpiece and tool interface, but that interface, access of that interface is very difficult here. So, you need very high sensitive instrument, that is load cell or the dynamometer or different type of acoustic emission sensors, in such a way that it can measure the small amount of forces or any type of other vibration signal or any type of tool wear signal. So, those things should be there, and size should be also very small, because you have to accommodate all these sensors or monitoring devices in a small location. So, these are the different problems or the different methodology by which you can successfully machine the micro component. So, what are the advantages of this particular thing, that after comparing this micro machining and the macro machining, we can find out that what are the ways. So, here what is the good thing, that do not require expensive setups and relatively quick, because we know the conventional machining. So, it is just a scale down of the conventional machining. We know that how to do turning operation, how to do milling operation, same operation is here, but we have to actually look into more detail. So, setups are not expensive, relatively quick, because we know all the basic or the kinematic structure of the machine tool, which are very same. No need for expensive mass and cost effective. So, this is related to actually the lithographic processes. Lithographic process, so that is MEMS based. That we have seen in the probably first class or the second class, comparison between the conventional this micro machining, mechanical micro machining, and the MEMS based the processes. So, here you need a mask for passing the light through it, so that it will actually remove some of the portion of that different type of surfaces. Then there is a etching of the surface, and then you can get some type of features. So, those things are called the MEMS based surfaces. Then suitable for individual component rather than the batch size, because if you use this MEMS based surface, it is for mass production, because in a single silicon wafer you can create hundreds, thousands or more than lakhs of components in the single wafer, but this is mostly used for the individual component rather than the batch size. And more advantage, you can actually create the real 3D freeform surfaces in one setup, and that is very difficult or sometimes not possible by any other process, let it be a lithographic processes or any type of other advanced machining processes like electro discharge machining, electrochemical machining, or the laser based machining. So, production of the micro injection mold for biomedical implants or the devices, you can actually create a 3D mold, and then this injection molding or the some type of other casting, micro castings are very easy if you are getting a mold at the 3D surfaces. So, that is the very big advantage of this particular micro machining part. and mostly you can do any type of machining of material, because only thing that you have a right tool for a right material. Metallic material, composite, polymer, ceramic material, anything can be machined by this particular micro machining process, because if our tool is harder than the workpiece, then there is no limit, only we have to look into the tool wear of the part. So, that is the advantages. Limitations are also there, because nothing is perfect. Size and accuracy constrained by the tool geometry, because what is the small feature you can create, that depends on the tool geometry. If smaller the tool, smaller the features you can create, but the tool geometry is also important, because we have to maintain the cutting edge radius smaller than the uncut chip thickness. So, that is the first thing we have to look into the detail of the cutting edge. Tool wear and breakage is very frequent in this case. Breakage is frequent compared to tool wear. Issue with the surface quality, finish and burrs, because if you are getting these particular things in the negative direction, then it is very difficult to remove those artifacts at the later stage. Material grains are also important here, that is related to both the side, that means not onto the workpiece side, but on the tool side also. But still less knowledge of appropriate machining conditions and values available for a different task. Because if you see our conventional machining, there are different design data books available, you keep the select the workpiece and the tool material, then there are specific speed feed and depth of cut calculations available for optimum removal, but that is not available right now in the micro machining. So, mostly you have to do trial and error, and you have to create your own database, so that later on that can be useful for others also. Now, this is also important, how to handle these micro components. Once you machine all the components, everything is ready, now how to transfer that component from one location to another location, because size is very small, and then it is creating a problem. So, handling, assembling and testing of the small micro machine components is very difficult. So, if you see this thing, then once your machining is over, then you have to use some type of very gentle pluckers to move this component, but that also depends that what is the size of these things. Then there are some components available which are piezoelectrically actuated, that it will not create so much of force that it will actually damage the component or the machine component to a large extent. Then there are some vacuum type of tweezer available, that it is a vacuum type. So, you just touch the surface, it will pluck up that part completely, and you do not require any type of forces. So, micro components can be fragile and difficult to see and handle. So, special instrumentation and packagings are required. So, this is the some of the ways of handling these components, and in some cases the micro components have handling features incorporated into their structure that may needed to be removed in the post processing. So, this is similar to the adding that additional material for the burr removal process. So, you add some extra material, and that material will be helpful. Suppose now see, when you are doing a casting or molding of a plastic, this particular thing, suppose you consider this particular gear. So, now this is the gear, consider, let me draw it further, something like this, and hole is at the center. Now, when you are making that, what you provide, that you provide one extra feature here, right. So, you create these features here, then you mold it, then what is happened, the molded component will be completely this part, and then this contact zone is very small. So, you just if you bend this part, now it will completely come out of this part. So, these are the additional features you have to create just for handling of this part. Now, if you see these videos, let me show you this part. So, there are two different ways. Now, if you see, this is one of the vacuum holder. Right, and these are the different nozzles available if depending on the size. Now, if you see, so you can change this particular nozzle depending on the what is the size of the component you want to pick up. And then because of this air, then it will just suck, and you press this button, it will release this particular part. So, that is the advantage of using this part. This is about the small component, but if you have large component area, then you can also use a similar way, but now the area of this particular part is large. So, this is again the same vacuum type of things, but its area is large. So, this is the way you can actually move this component, and you can move to the different location. Advantage of here is also one of the things that you can actually change the pressure of this particular part. So, how much pressure is required? So, this is a vacuum level, maximum, minimum is there. So, depending on the delicacy of this component, if it is very delicate, then what you can do, you can actually minimize the pressure, so that it will not damage the component here, and this way you can move the component. So, these are vacuum based components, and these vacuum based components are very handy in the fabrication of these particular parts. So, this is all about the machining or comparison between the micro machining zone and the macro machining zone. We have seen about all the things on the mechanics point of view. We have seen about the how to handle these components, and we have also seen that how the errors and other things are generated. So, let me finish this lecture here, and we will continue about the component of the machine tools in the next class. Thank you very much.